Good morning, children. Today, in the second lecture of the chapter Current Electricity, I am going to cover the following topics: Ohm's law and its limitations, resistivity and factors affecting it, temperature dependence of resistivity, carbon resistors, electrical energy and power, series and parallel combination of resistors. Now, Ohm's law. Now, you are quite familiar with the Ohm's law. You have studied in class 10th also. According to Ohm's law, when I current is flowing through a conductor across which a V potential difference is applied, then V is proportional to I and V is equal to Ri. Here, R is called the resistance of the conductor. The unit of the resistance is ohm and its symbol is omega. Ohm, just like this. Now, this resistance R not only depends on the material of the conductor, but it also depends upon the dimensions of the conductor. That means R is equal to rho L upon A, where L is the length of the conductor and A is the area of cross section of the conductor. Rho is the specific resistance of the conductor. So, R depends not only on the material but also on its dimensions. Now, limitations of the Ohm's law. That means that relation V is equal to IR is not strictly obeyed in all conditions. Means in some condition it does not follow. The first condition is this, that potential difference may vary non-linearly with the current. It means now when the current is passing through the conductor, and if we draw a graph between V and I, we find that it always comes in a straight line shown by the dotted line. But if the current flows through the conductor continuously for a longer time, then we find that the graph is slightly in the shape of curve. That is, further it is not in a straight line, it has changed to a curve shown by the continuous line. Because this happens, so now it is curved towards the upper side, it shows that the resistance of the conductor is increased. So because this happens, because when the temperature increases, then resistance of the conductor increases, the slope is increased, which shows that the resistance of the conductor is increased. So when the temperature increases, then V is equal to IR is not followed. Similarly, if for some conductors, for the positive potential difference and for negative potential difference, the behavior of the change of the current is not same. So this is the characteristic curve of a diode, in which the negative and the positive values of the voltage and the current, you can say that here the current is changing in a different manner, but for the negative potential the current is changing in a different manner. So the variation of the current with potential difference depend upon the sign of the potential difference applied. Similarly, in this graph, you can see that for the two at this point and at this point, there are the two values of the voltage for the same value of the current. So this is a different type of material which is showing the two values of the current, two values of the potential difference for a same value of the current. Or we can say that at this position the slope is positive, while at this position the slope is negative. So such type of behavior is shown by a material which is known as the gallium arsenide. So here in all these three conditions we can say that Ohm's law is not following. So the material or the conductors in which the V is directly proportional to I and the graph is a straight line, they are known as the ohmic conductors, and for which the graph is not a straight line, they are called the non-ohmic resistors. Now, resistivity of a specific resistivity or specific resistance of a conductor. Now, as we know that R is equal to rho L upon A. So from here we can say that rho is equal to R A upon L. Here rho is called the resistivity or the specific resistance. Now from this expression, if we take A is equal to 1 meter square, and if we take length of the conductor 1 meter, then from this relation we will come that rho is equal to R. So we can say that this rho is the specific resistance of a conductor whose area of cross section is 1 meter square and length is 1 meter. So numerically we can say that specific resistance or the resistivity is equal to the resistance of a conductor of unit length and unit cross sectional area. The value of resistivity does not depend upon the dimensions of the conductor. It depends only on the material. This is very important point to remember. Many MCQs are based on this concept. According to it, if you take the two conductors of different length and different A value of A having the same material, means if you are taking the two conductors of the copper having different length, even then their resistivity will remain same, only the resistance will change. But if you take the two identical conductors of different material, that is one of copper and one is iron, then their resistivity will be different, because resistivity does not depend upon the dimension, it depends only on the material. Now, factors affecting electrical resistivity. In the previous lecture 1, you have come to the expression Vd, that is the drift velocity E tau upon m, and one more expression that I is equal to NAVD E. Now if you substitute the value of Vd in this expression, then this expression will reduce to this one, and as also you know that E is equal to V upon L. So from here you can put the value of E and the expression further reduced to this. Rearrange this expression, V upon I is equal to ml upon N square tau A, and but V upon I is R, V upon I is equal to R. So in place of this you can write R and substitute simplify it. Also R is rho L upon A. So from both the terms equations we can come that rho is equal to m upon N square tau. So from this expression we can say that the specific electrical resistivity depends upon the number of free electrons and the relaxation time, as m and E both are constants. So we can say that rho depends upon n and tau. Now number of free electrons and the relaxation time both may change with the temperature. If you increase the temperature, the number of free electrons definitely it will increase and the relaxation time will decrease. So depending upon the temperature, the resistivity also changes. So now let us consider or discuss the temperature dependence of the resistivity. Now resistivity of a material is dependent on temperature. Experimentally, it is found that resistivity of conductor increases with the increase in temperature, and according to this expression, rho is equal to rho naught 1 plus alpha T minus T naught, where rho is the specific resistance at temperature T, rho naught is the specific resistance at temperature T naught, which is a reference temperature, and alpha is the coefficient of resistivity. Now let us discuss it for the different materials, that is conductors, semiconductors, insulators, etc. Now for the conductors, alpha is positive. Now if the temperature of the conductor increases, so the average kinetic energy of the electrons in the conductor increases, and since they collide frequently, so definitely the relaxation time tau will decrease. So from this relation we can say that n increases and tau decreases, so resistivity increases. So we can say that as the temperature increases, the resistivity of the conductors increases. In case of an alloy means the mixture of the two metals. So in mixture of the two metals, the resistivity is very large and it has a very weak dependence on the temperature. The value of alpha is very small, that is why it is an excellent substance to be used for the conductors for the construction of a standard resistance coils. Means some instruments which are used in the labs in which some resistors are used, they are made from some alloy. In case of the metal, the resistivity increases with the temperature, but in case of an alloy, the value of alpha is very small. They are weak dependence on the temperature. For semiconductors or insulators. The resistivity decreases with the increase in temperature exponentially. As the temperature increases, N increases and tau decreases. So from this relation, as N increases and tau decreases, so but increase in N is dominant with the decreasing tau. So N is more increases. So as a result, overall result, the resistivity decreases. Hence, we can say the resistivity of the semiconductors and the insulators decreases with the increase in temperature. Now, in case of the graph, if we discuss the same thing with the graph, for the case of the metals, if we draw a graph between rho and temperature, then we find that for considerably the range of the temperature, the graph is linear, means rho increases, resistivity increases linearly with the temperature. But at for a very low temperature, this linear dependence is not linear, or this dependence is not linear. In case of nichrome or the alloy, the graph between rho and T will be shown as this, that is as a function of the absolute temperature. In case of the semiconductors, the temperature dependence, because the resistivity decreases, so decreases, the graph will be like this. So in this way, we can say that for the metals, the resistivity increases with the increase in temperature. For the alloy, there is a very weak dependence on the temperature. In case of the semiconductors, the resistivity decreases with the increase in temperature. As the resistance is directly proportional to the resistivity of the material. So, expression can also be written as RT is equal to R naught 1 plus alpha T minus T naught. So, from this expression, we can write the expression for the temperature coefficient as 1 upon R naught del R upon del T. Now, this carbon resistors I am going to take in the second part.